partition of a closed interval. Partition of a closed interval. Okay. So here we can see in the textbook the symbol is like this, that is partition P is equals to, we have the closed interval A comma B. So if A comma B is a closed interval and if we divide, if A comma B is a closed interval and if we divide A comma B into n parts such that A is equals to x naught less than x1 less than x2 so on up till xn is equals to b. Okay. So this we call it, and this is called as a partition and we represent it as, that is P is equals to A is equals to x naught comma x1 comma x2 so on up till xn is equals to b. Okay. So this is called, so in problems wherever the Riemann integrability problems are there, there you will see representation of P will be there with respect of closed interval A comma B. Okay. So the definition of the partition of a closed interval is that whatever the interval is given, that interval is divided into n parts such that first whatever the point is there, that point is equals to x naught, means each term of that will be in the form of one term is less than the other term. Okay, x naught is less than x1, x1 is less than x2 up till it is equals to the last point. And this is the main representation of the partition. Okay, so here whatever the elements are there, we can write these all whatever the elements are there into subintervals. Okay, so and those subintervals are like this, we'll write x naught comma, means this is the main interval. From this interval these are the elements. From these elements we are writing the subintervals, that is x naught comma x1, after that x1 comma x2, next x2 comma x3, so on. These are what are we are writing as like this, these are called as a subintervals. Okay, so on up till xn minus 1 comma xn are called n subintervals. N subintervals of closed interval A comma B. Okay, and this is the main thing important. This is called as a length of rth subinterval. These all concepts in solving the theorems, these are useful. Okay, so Riemann integrability in that partition is important. You will see the symbol of this one, and also like these elements will be there. These elements are called as a subintervals. Okay, and the length of rth subintervals is represented as like this, that is x r minus 1 comma xr. Okay, and it is denoted as this is the main symbol. Okay, delta, small delta to the base r. This is called, wherever the representation is there, this is called as the length of subinterval. Delta r is equals to, this is the formula. Okay, xr minus xr minus 1. Okay, for solving the problem and also for solving the theorems, we use the concept of length of subintervals, that is small delta r is equals to xr minus xr minus 1. So for this you can see the example here, that is whenever any closed interval is given, so delta, small delta r is equals to xr minus xr minus 1. So we can take one example. If the closed interval is given as like this, example closed interval is 1 comma 4. So for this, the subintervals are 1 comma 2, 2 comma 3, next 3 comma 4. Okay. So like this, these are the subintervals. If you want to find that is the length of the subinterval, then for this subinterval, that is delta r is equals to 2 minus 1 equals to 1. Here delta r is equals to, that is 3 minus 2 equals to 1. Here delta r is equals to 4 minus 3 equals to 1. Okay. So like this we can find the length of the subintervals with the help of any given the closed interval. Okay. So in this, one more important thing is norm of a partition. Norm of a partition, this is also you can see in many theorems. And even on this, you may get the small 5 marks problems also will be there. Norm of partition. Okay, norm of partition means the maximum length of subintervals. The maximum length of subintervals is called norm of partition. Okay, and the representation of this is, and it is denoted as like this. Like these two lines and P. So it is called as norm of partition P. So for this you can see one example. So this norm of P is represented as, it is represented as like this and defined as, so defined as norm P is equals to maximum of, that is delta R, that is length of subintervals. So maximum of length of subintervals is called as a norm of P. Okay. So you can take one example, that is if the closed interval is given as 0 comma 5. So for this one, if he is asked to find the norm of P, then first you write here the elements of P is equals to, that is A is here 0 and B is 5. So that means the whatever the elements will be there, those terms will be here 0 comma 1 comma 2 comma 3 4 and 5. Okay, this is A and this is B, and the other terms are x1 x2 x3 x4 terms. So here for this we know to that how to find the delta R. That is, if you take the subintervals, you will get the subintervals as like this. Subintervals. So subintervals are, first one is 0 comma 1, second one is 1 comma 2, next 2 comma 3, next it is 3 comma 4, and last one is 4 comma 5. Okay, these are the subintervals of the given closed interval 0 comma 5. So if you find the delta R, then delta R will be for this one, the value, that is for 0 you are finding. So delta 0 means that is 1 minus 0, you will get 1. 2 minus 1 means 1, you will get 3 minus 2 means 1. 4 minus 3 equals to 1. Like that you will get all the values here. So R is, this is XR minus 1, this is XR. So R value is here 1. So you will get it as 1, that is delta 1 is equals to 1 minus 0, 1. Next, delta 2 is equals to 2 minus 1 equals to 1. You are able to see here. So I will write above. So delta 1 is equals to 1 minus 0 equals to 1. Next delta 2 is equals to 2 minus 1 equals to 1. Next delta 3 is equals to 3 minus 2 equals to 1. Delta 4 is equals to 4 minus 3 equals to 1. Delta 5 is equals to 5 minus 4 equals to 1. Okay. So with all these terms, we have got the length of the subintervals. So what is norm of P? If is asked to find norm of P here, this is the closed interval. And if is asked to find norm P, okay. So the norm of P is equals to, it is the maximum of whatever the dr, that means the length of the subintervals are, that is delta 1 comma delta 2 delta 3 comma delta 4 comma delta 5. If you take those all values, it is the maximum of 1 comma 1 comma 1 comma 1. So these all the values we got as 1, no, that you are writing. So the maximum of all these ones is only 1, no. So norm of that partition P is 1 here. So like this, we have to find the norm of the partition. The main thing is you should know the definition of this one, and this whatever the representation is there. This is the very important in solving the problems and also in doing the proof for the some theorems. Okay. So next we have that is if f is bounded in a closed interval a comma b, then function is bounded in every subinterval a comma b. So here same small m and capital M are represented as a, if f is bounded in closed interval, then we have the same, that is small m and capital M are represented as infimum and supremum. Okay. Here the representation of the supremum and infimum of closed interval a comma b, whatever it is given, no, that is important for solving the theorems here. Okay, that is here m is called as infimum, small m. The small m is called infimum of f in closed interval a comma b. Okay. Capital M is called supremum of f in closed interval. Okay. So the representation of this is very important. That is small m is equals to infimum of f of x such that x belongs to closed interval a comma b. Okay. So like this representation is called as a infimum, and also capital M is called as a supremum of f of x such that x belongs to closed interval a comma b. So this is the, whatever the m is there, this is the least value. Okay. This is the maximum value, or we can write greatest value. So small is the, what small m is called as the least value, and capital M is called as the greatest value of the given function here. Okay. And here this representation also will be there. If small m r and capital M r and supremum in rth subinterval. Okay. R infimum and supremum in rth subinterval. That is xr minus 1 comma xr. Okay. This is very important. So in solving the whatever the theorems are there, there you will have the representation of small mr and capital MR. So these are defined from the infimum and supremum, and these are the same infimum and supremum of in whatever the function is there f of x in rth subinterval, that is xr minus 1 comma xr. Okay. So and one thing is every time infimum is the least value, no? So every time infimum will be less than or equals to supremum. This is the important one. Infimum will be less than or equals to supremum, or else we can type MR value is always less than or equals to capital MR value. Or if you take this, M is less than or equals to capital M. Okay. So these concepts are useful in solving the some problems and also theorems. So infimum will never exceed the supremum. So infimum will be every time least value only than supremum value. Okay. So next we have Darbox sums are there. Darbox sums. So if you see the textbook, you will have these all concepts. On these concepts only you have theorems are there. Okay. Just if you understand what are these concepts, you can easily do the proof of these theorems. Okay. So Darbox sum is if a function, you can see the definition. I am not writing the definition, just a representation of this I am writing. Okay. If a function f is defined in closed interval a comma b and bounded, and any partition of this interval is p is equals to a equals to x naught comma x1 comma xn equals to b, then sum. Okay, this sum will write it as u f comma p. Okay, f is the function, p is the partition here. Okay, it is equals to summation n equals to 1 to infinity capital mr xr minus xr minus 1. Okay, or else it is equals to summation n equals to 1 to infinity capital mr. This is nothing but delta r. Okay, this is small delta r. This is called as upper Darbox sum. So this is called upper Darbox sum. Okay, you are able to see. This is called upper Darbox sum. So in this we have the supremum. Capital MR is the supremum, no? So supremum of representation of the length of subintervals delta R with respect to your summation n equals to 1 to infinity is called as the upper Darbox sum. Okay. So one more sum is there. It is the lower Darbox sum. Lower Darbox sum means L will be their representation. L f of p is equals to summation n equals to 1 to infinity small mr xr minus r minus 1. Okay, that is called as lower Darbox sum. So L f comma p is equals to summation n equals to 1 to infinity small mr xr minus xr minus 1. So it is equals to summation n equals to 1 to infinity small mr delta r. So this is lower Darbox sum. Okay. From this upper and lower Darbox sum only, we can see that we have one theorem very important which you will get for the 10 marks question. That is the Darbox theorem is there. So the theorem is important. So state and prove Darbox theorem will be there. That is the 11th A question. 11th A or 11th B question you may get from this one. Okay. So this is the representation of both the upper Darbox sum and also lower Darbox sum. And one more you can see here. This is the just you see the representation, that is the summation n equals to 1 to infinity small m into, if we have here delta r is there, that is delta r is equals to, we will have this one for solving the problems. This will be into capital M into B minus A. And one more is small m into B minus A. Okay. These two concepts we will use in some theorems. And one more concept we have in this, that is the lower Riemann integration and also upper Riemann integration will be there. So these two are very important. You can see them. So in solving some theorems, we will use these concepts. So wherever the symbols are there, you can use those two symbols here. Next, upper and lower Riemann integrals. So whenever any given function is satisfying the conditions of the integrability, Riemann integrability, if it is satisfying the conditions, then we say that the function is a Riemann integrable function. Okay. For that one, whatever the lower Riemann integration and also upper Riemann integration values, if both are same, then the given function will be a Riemann integrable function. Okay. That on that you will have the theorems, that is f is a any function such that if it is satisfying the conditions of the Riemann integrability, then mod f will be another function such that it also satisfy the condition of Riemann integrability. You can see the theorems in your textbook. On this condition of Riemann integrability only, there you will have lower Riemann integration and also upper Riemann integration. If both those two values are same, then we say that the given function is Riemann integrable function. Okay. Many theorems are there. F is a function, mod f is another function. Next we have f square is also there. F square is show that f square. So whenever a function is Riemann integrable, that representation will be there. So that representation should be also, you should know how to represent the Riemann integrability. Okay. Upper Riemann integrable, upper Riemann integral. So how we'll represent that one? So you have the definition in your textbook. See that one. Just I am giving the representation of that one. Infimum and Orbox on UP of S. So like this it will be there. A to B. Integral, no? So integration symbol. This is the lower integral and also this is the upper integral. So whenever upper integral you have like this, it is called as upper Riemann integral. Okay. So f of x dx is equals to infimum of upper Darbox sum f of comma p such that p belongs to p of closed interval a comma b. So like this. So this is called as upper Riemann integral, that is a to b f of x dx equals to upper Riemann integral. So here you can see the representation of here upper integral will be, you will have on that dash will be there. So this is the main representation of this one and it is defined as infimum of upper Darbox sum. Just now we have seen the definition of upper Darbox. So whatever the elements are there in this, of that smallest element, which your infimum is nothing but the smallest element, no? From this, if you will take whatever the smallest element, that smallest element will be the upper Riemann integral. Okay, this is the definition of upper Riemann integral. Next, lower Riemann integral. So lower Riemann integral means in the whatever the lower integral will be there, that is lower limit. you will have the dash here. Okay, a to b f of x dx. As we know from the limits, that is integration part we have seen in second semester, you know this is the lower limit and this is the upper limit. So for the upper limit, whenever the dash is symbol is there, it represents upper Riemann sum. For the lower limit, if you have the dash, it is represented as a lower Riemann integral. Okay. So it is equals to supremum of L f comma p such that p belongs to, this is like this, you should write 2. Okay. P of a comma b, that is supremum of, this is the lower Darboux sum. Supremum of lower Darboux sum is called as a lower Riemann integral. That is, whatever the lower Darboux elements are there, in that highest value if you take, that is called as a lower Riemann integral. Okay. So this condition should be satisfied, and also this condition, if it is satisfied, when these two values are same, that is lower and also upper Riemann integral values both are same, then we call that the function is satisfying the conditions of Riemann integrability. Then we call the function is Riemann integral function. Okay. So this conditions, when it is satisfying, how we called the function, for that you have one theorem. It is the necessary and sufficient condition to show that a function is Riemann integrable. This is also the 10 marks question and very important one. So either you may get this one for 10 marks, or the one more is, that is the Darboux theorem will be there. The two, anyone you will get for 10 marks question. The condition of Riemann integrability is, that is upper Riemann integral and lower Riemann integral should be equal. So your main thing is, when we call a function is Riemann integral means, so Riemann integral means this, whatever the Riemann integrability is there, no, for this condition is should be equal to a to b f of x dx. And whenever any function is Riemann integral means we represent it as f belongs to R of a comma b. Okay. This is the representation that a function is Riemann integrable. This f belongs to R of a comma b means this is the representation, that is a function is Riemann integrable. Here if belongs to symbol is there, no, if we have like this not equals to means the function is not Riemann integrable. If you see in textbook, you will have these symbols. So f belongs to R of a comma b. So in this necessary and sufficient condition theorem is, page number I will take. Page number 92. Page number 92, 7.3 is there, no, conditions for Riemann integrability. So there we have, so question will be asked like this. If it is asked for 10 marks, it will be state and prove necessary and sufficient conditions for a function to be Riemann integrable over closed interval a comma b. So the question will be like this. So for the proof is here 92 page number. You have to write the statement. A statement is, a bounded function f mapping from a closed interval a comma b to R is Riemann integrable if and only if for any epsilon greater than 0 there exists a partition P of closed interval a comma b such that u p of, that is upper Darboux sum minus lower Darboux sum if it is less than epsilon. This is the main condition to tell that any function is Riemann integrable. Okay. So one more important is, we have Darboux theorem is there. Its statement and also proof will be asked in the examination. Box theorem. So the condition for just I am writing the symbol for this one, that is how to represent the definition of the Darbox theorem, that is U P comma F is less than, that is upper Darbox sum f of x dx plus epsilon. Okay, this is L P comma F is greater than A to B f of x dx plus epsilon. Okay, necessary and sufficient condition is U P comma F minus L P comma F is less than epsilon. This is the condition of integrability. Okay, and the condition of for the Darbox theorem is this one. In page number, this is minus epsilon. This is in page number 90. So theorem proof is there, no? This is the important one. This is the upper Darbox sum is less than upper Riemann integrable. Lower Darbox sum is greater than lower Riemann integration. Then if these conditions are satisfied, then Darbox theorem is verified. Okay, and this is the condition of integrability. That is upper Darbox sum minus lower Darbox sum. Whenever it is less than epsilon, this is the condition for the Riemann integrability. So on this we have one problem. So it might be asked for the 5 marks question. So if you see 7th unit whole, you have theorems are there. That is, let f be defined on closed interval 0 comma 1 by f of x equals to 1 if x is rational and it is equals to minus 1 if x is irrational. So that f is not Riemann integrable over 0 comma 1. Does not symbol is there. Does not symbol is there means it is not satisfying the condition of Riemann integrability. So problem is, let f be defined on closed interval 0 comma 1 by f of x equals to 1 if x is rational. Minus 1 if x is irrational. Okay. Show that f does not belongs to R of closed interval a comma b. That means we have to show that it is not Riemann integrable. Okay. So whenever it is the condition first one is that the whatever the function is there, that function will be bounded on closed interval. F is bounded on closed interval 0 comma 1. Okay. Let P is equals to, partition means first term is what? 0. 0 is equals to x naught, x1, x2, so on up till xn is equals to 1. Okay. First element is this and last element is this. This is the representation of the partition. Be a partition on closed interval 0 comma 1. Okay. Then, so our function, how it is defined, function f of x is defined as 1. When it is defined when x is rational. So whenever x is a rational number, we have the definition of the function is 1. And f of x equals to minus 1 if the function, whatever the value of x is there, no, that x value is irrational. Whenever we are taking it as irrational number, the value is minus 1. Whenever we are taking the x value as a rational number, the value is 1. So here, whatever the elements are there in this, the there is a capital M and also small m. Capital M is the supremum and small m is the infimum here. So these two are the elements present in the function f. The condition is when it is rational and the condition is when it is irrational. So here mi value, that is supremum value is highest value in 1 comma minus 1 is 1. No? So supremum is 1 and small I, that is the infimum value is minus 1 here on closed interval a comma b. Okay. So first thing you have to do. Now we have to find what is the Darbox sum, upper Darbox sum and also lower Darbox sum. So upper Darbox sum is u p comma f equals to, we have the definition summation n equals to 1 to infinity. So we are taking here I, here I representation is there, no? So summation I equals to 1 to n, 1 to n mi comma delta I. Okay. So instead of r, we are taking here small I. Either you can write r equals to 1 to n or I equals to 1 to n. So here you have to substitute the value. What is the mi value? Mi value is 1. That is, it is equals to summation I equals to 1 to n. This value is 1, 1 into delta I. Okay. So delta I value means only one element is there, no? So delta I of this one will be 1 only. So 1 into delta I is equals to 1. Okay. Next, LP comma F. LP comma F equals to summation I equals to 1 to n small I delta I. So it is equals to summation I equals to 1 to n. What is our small mi value? It is minus 1. So minus 1 into delta I. So the length of subinterval of this, whatever the element of 1 is there, no, that will be 1 only, and minus 1, you will have the same element. So minus 1 into delta I value will be minus 1. So here upper door box sum value is 1 and also lower door box sum value is minus 1. We know that to show that any function is Riemann integrable, upper Riemann integrable and also lower Riemann integrable value should be same. Okay. So that is here lower limit is 0, upper limit is 1 here. So f of x dx is equals to infimum of u p comma f. Okay. So 0 to 1 f of x dx is equals to, just now we have seen the definition, no? Are you able to see this one? Upper Riemann sum and lower Riemann sum, we have seen the definition of Riemann integrability. So A to B, that is 0 to 1, infimum of, this is upper Riemann integral. So upper Riemann integral f of x dx is equals to infimum of, that is u p comma f. So infimum of, what is UPF value? UPF value is 1. That is, this value is 1 here. So only one element is there. So that element is 1. So infimum means least element. So only one element is there. That is only the least element, and that whatever the element is there, that is only the highest element. So infimum of 1 is what? You will get the 1 only. And when you will see the supremum of this one, that is lower Riemann integral, is equals to supremum of LP comma F. Supremum of LP comma F value is what? Minus 1. Okay. Supremum of. So this is only the high. Just now we have seen, no, this is the only highest value and also only one element is there. So this is only the highest value and also that is only the least value. So here we get the supremum of that value is equals to -1. So therefore, integration of 0 to 1 f of x dx is not equals to 0 to 1 f of x dx. That is, upper Riemann integral is not equals to lower Riemann integral. Therefore, f is not Riemann integral. Therefore, f is not Riemann integral over 0, comma 1. Okay. So like this, you have to solve the problem. First thing is find the upper Darboux sum and also lower Darboux sum. And after that, find the lower Riemann integral and also upper Riemann integral. If both the values are same, then it is Riemann integral. If both the values are different, means it is not Riemann integral. Okay. So in this, just now we will see what are the important theorems in this unit. So 90 page number Darboux theorem we have seen already. 92 page number conditions for Riemann integral. And 93 page number 7.3.2. So it is 5 marks question. That is, if f is continuous on a comma b, then f belongs to R a comma b. That means the main question will be asked like this. Show that every continuous function is Riemann integral. Page number 98, you have no MEQ questions. So there you have section B. These are the short answers that will be for the 5 marks question. Okay. Show that every continuous function is Riemann integral. So for this, the solution is 7.3.2. Next, one more theorem, 5 marks is 94 page number 7.3.3. If f is mapping from closed interval a comma b to R is monotonic on closed interval a comma b, then f belongs to R of closed interval a comma b. Okay. This question, it is not asked directly like this. The question will be, prove that every monotonic function is Riemann integrable. Okay. So for that, proof is 94 page number. And one more in 95 page number, check your progress. You have no 7.3.4. This is also asked for 5 marks question. Show that a continuous function is Riemann integrable. So 98 page number, first question, second question. Both are for, that is a 10 marks question. That is, question will be first question. Last sentence is there, no, state and prove necessary and sufficient conditions for a function to be Riemann integrable. Only this part will be asked for 10 marks. Second one is state and prove Darboux theorem on Riemann integrals. These two theorems and also small theorem, 5 marks theorems are short answers, section B 1 and 2. Okay. These are the 11th A and 11th B questions and also their 4th and 5th questions. Next, unit 8, we have fundamental theorem of integral calculus. In this 102 page number, you have no 8.2.7. This is the 10th question. That is 10 marks question will be asked. 11th B question. So question will be state and prove fundamental theorem of integral calculus. Okay. This proof is you have in page number 102 and 103. This is a very important one. So only one theorem you have in this unit, important one. So you can see the question framing 105 page number, state and prove the fundamental theorem of integral calculus. Next, in the mean value theorem of integral calculus, in this problems are there. That is one 5 marks problem you will get from this one. So page number 111 we have 9.3.6. So like these problems How many problems are there? Means 1, 2, 3, 9.3.8. And also even in model examination questions, we have first and second problem. So from these any one, you will get for 5 marks question. Tomorrow in your schedule, you have maths online class. Huh? So anyone can respond. Shravani,
తెలీదు మ్యామ్. రేపు
మీకు
ఉందో లేదో.
ఇచ్చిన షెడ్యూల్లో మీకు మ్యాథ్స్ క్లాస్ ఉందా రేపు?
నో మేడం, చూడలేదు.
ఓకే, యాక్చువల్గా మనకి ఓన్లీ 6 క్లాసెస్ ఉంటాయి ఆన్లైన్ క్లాసెస్. టుడే ఇట్ ఈస్ ద 6th క్లాస్. ఆల్రెడీ ఇట్ స్టార్టెడ్ ఫ్రమ్ 18th నుండి స్టార్ట్ అయ్యాయి కదా మనకి.
ఎస్ మేడం.
సో ఈ రోజు వరకు అయితే యాక్చువల్గా లాస్ట్, కానీ మాకు ఇచ్చిన షెడ్యూల్లో కూడా రేపు క్లాస్ ఉంది అండ్ 15th రోజు కూడా డేట్స్ అయితే ఇచ్చారు. అంటే వీఆర్ నాట్ ష్యూర్ అనమాట. అంటే రేపు ఉండొచ్చా ఉండకపోవచ్చో కూడా తెలియదు. ఇఫ్ ఏమన్నా ఉంటే రేపు మనం ఒకసారి ఇంపార్టెంట్ క్వశ్చన్స్ అన్ని చూద్దాము. సో
ఓకే మేడం.
ఆల్మోస్ట్ యూనిట్స్ చెప్పినప్పుడు అన్ని ఇంపార్టెంట్ క్వశ్చన్స్ అయితే చెప్తున్నాను నేను. ఒకసారి మీరు చూసుకోండి. మీకు ఆల్రెడీ డౌన్లోడ్ అయిన ఉంటున్నాయి కదా లెసన్స్, అందులో మీరు ఒకసారి ప్రిఫర్ చేస్తే అన్ని ఇంపార్టెంట్ క్వశ్చన్స్ తెలుస్తాయి మీకు.
ఉంది మేడం, మాకు కూడా ఇచ్చారు. 9:15 ఉంది క్లాస్.
9:15 ఉంది, కానీ కంపల్సరీ షెడ్యూల్ అంటే ఒక్కొక్క సెమిస్టర్ కి 6 క్లాసెస్ మాత్రమే ఉంటాయి ఆన్లైన్.
ఎస్ మ్యామ్.
ఇంకో 2 ఎక్స్ట్రా ఉన్నాయి, అది మళ్ళీ కన్సిడర్ చేస్తారా లేదా, రేపు ఉంటుందో లేదో మనకు ఐడియా లేదు. ఒకవేళ ఉంటే చూద్దాము ఇన్ కేస్.
ఓకే
అంటే మీకు
మేడం.
ఒక ఎంఎల్ అండ్ లాంగ్వేజ్ ఇవి ఆన్లైన్ క్లాసెస్ జరగలేదంట కదా?
నో, తెలియదు మేడం, అవి జరిగినాయో లేదా అంటే వినలేదు.
అవునా, యాక్చువల్గా ఆ డేట్స్ ఇచ్చారు అని అన్నారు. ఓకే, సో జస్ట్ 10th అండ్ 11th యూనిట్ లో ఒకసారి నేను ఇంపార్టెంట్ అయితే చెప్తాను. రేపు మనం 9th యూనిట్ లో ప్రాబ్లమ్స్ చూద్దాం ఒకసారి.
ఓకే మేడం.
10th యూనిట్ 122 page number, 10.4.1 and even 10.4.2. So these two are the 10 marks questions. Next, 124 page number, 10.4.5. So this problem may be asked for 5 marks question. 10.4.5. Even 10.4.6 also. 10.4.6. So 128 page number, if you'll see, means the question framing will be like this. Part B is there, no? First question and second question. Show that point-wise convergence of sequence of functions and finite set is uniform. State and prove that uniform convergence of a sequence of functions preserves continuity. And part A, first question is there, no? State the definition of point-wise convergence. This will be asked for 10 marks question. So below questions you may get for 5 or 10 marks. Next we have unit 11, infinite series of functions. So in this 131 page number, 11.2.1, this is the 10 marks theorem. 11.2.1, 133 page number. You have problems, even example problem is there, 11.2.3. And most important and regularly asked question is 135 page number, Weierstrass M-test theorem. Okay, if you see the previous question papers, in that compulsory 12th A or 12th B question will be this one. So statement and proof will be very small, but it is regularly asked question. Okay, so a theorem is Weierstrass M-test. The example for this you have in 11.3.2. Okay, combination of these two means give one example also they may ask. So in the down you have the one example problem, simple one it is there. And 136 page number 11.3.3. This is the 5 marks problem. And 137 page number section A, you can see long answer, that is the state and prove waste stress M test. Second theorem. And page number 138, first and second question. Show that the following series is not uniformly convergent. And second one is show that the series is uniformly converges on alpha comma beta. Okay. Next in 139 page number, you have the 12th unit, that is power series we have. We have seen the problems in 5th unit and 6th unit, no? There is the infinite series. So whatever concepts we have learned there, from that concept only we'll solve the problems here, power series. So tomorrow if we have, so we'll see one problem on, that is a 8th unit, and one problem from the power series, 12th unit. So here radius of convergence will be there and also interval of convergence finding will be there in the power series. 141 page number 12.1.1 and 12.2.2. 12.2.1 is very important. So this is regularly asked for 10 marks. And one more is 12.2.2. So radius of convergence theorem will be there here. Just if you know the concept, it is enough for solving the problems. And one more important is 143 page number 12.3.4. So from these any theorems, you will get one for the 10 marks question. And here exercise problems are there. So these problems are important. Just they will ask eighth question. Section A will be there. No, in section A, eighth question will be from this unit. So any one problem may will be asked on radius of convergence or interval of convergence. Okay. So tomorrow we'll see problems on 8th unit and also 12th unit.
Okay, madam. Thank you.
Okay.